So we were talking a little bit about a transfer-based machine. And the idea was we had something like a standard digital memory with a series of locations. And in this memory, starting at location 0, we stored pairs of addresses. These are addresses in this memory. And beginning with a program counter value of 0, we read these first two addresses and we interpret it as an instruction which says transfer the contents of memory address source to memory address destination. So maybe this source destination pair say read the contents of this memory location and copy it here. And then we increment the PC by 2 and we find another source destination pair. And maybe this says take the contents of this memory location and copy it here. And then we go on to memory locations 4 and 5 and so on. And this looks in some way like a very long instruction word coded micro machine. Particularly if we map hardware into certain memory locations so we can do things like transfer things to the inputs or the outputs or the control registers of arithmetic units, I/O units, and so on. And also if we have certain addresses that we use for special purposes. For example, we might decide that this last address is the program counter. And so if we load a value into here, that becomes the address of the next instruction to execute. So we can do sequential execution, we can do loops, we can do conditionals, we can do all the things that we use in a regular programming language on a von Neumann machine. But the idea is to try to extend this basic model along a few different dimensions. And here's how we want to extend this. We're going to look at 3 different dimensions. One is simultaneous execution. Because this model does this instruction, then this, then this, then this, but let's try to make all these instructions happen at the same time. The second dimension is taking the time step and shrinking it to an infinitesimal time step. And the third is taking the spatial discretization of this memory and shrinking that to an infinitesimal dimension. So what does simultaneous execution mean? It means that we look at this entire memory as a sequence of instructions, but instead of executing them sequentially, we execute them all at the same time. Copy from the address specified here to the address here, copy from the address here to the address here. So all at the same time, this location's contents get transferred here, this location's contents gets transferred here, and so on. Well, that's kind of interesting. It's a little closer to how the universe works because the universe doesn't do one thing and then the next and the next. Throughout space, everything seems to happen at the same time. So we're kind of mimicking that behavior here with simultaneous execution. So this starts to look a little like a cellular automata, for example, where you have a series of elements and the clock ticks and everything gets updated. It's like a state machine. But when you do that, there's this discretization of time. Tick, tick, tick. And in between the ticks, things are settling, but things basically happen on this clock tick. So that's a delta t. How can we make that delta t smaller and smaller? And the idea is, while this source destination transfer is taking place, this source destination transfer is also taking place. But if we let the system move forward a very tiny amount in space, in time, and then reevaluate what these instructions are saying, and possibly change what the transfers are that are being called for by this program, if you will. So for example, this source destination pair says, take this location and copy it down to here. And at the same time, this source destination pair says, take this and copy it over here. Well, depending on the value here, we're changing this destination address. And so now this source destination pair is not saying go from here to here. It's saying go from here to whatever the new location of this destination is, possibly up here, or down here, or somewhere else. So we want to advance this system through very small time steps and allow the instructions to start changing each other and changing themselves. So that's discretization in time. The third component is discretization in space. Instead of having discrete addresses 0, 1, 2, 3, we could split this into twice as many memory cells and have address 0, 0.5, 1, 1.5, 2, 2.5, and so on. And now we need to store values in here that correspond to these whole or half numbers. But we could cut this into a lot smaller set of spaces. For example, we could cut each of those cells into hundredths. So this would be 0, 0.01, 0.02, all the way up to 0.99, and then 1.0, 1.01 to 1.99, 2.0, and so on. And each value inside one of these cells can now be a decimal number with 2 digits after the decimal point. So this might be 1.43, and the next location might be 2.75, and this is saying transfer the contents of this location to this location. So we start to break our space into smaller and smaller pieces, and we've gone from steps of 1 for the memory addresses to steps of 100th, but we could make it 1,000th or 1,000,000th or 1,000,000th, and the idea is to take it to an extreme where our delta x becomes infinitesimally 0. So we're trying to discretize, to de-discretize in 2 dimensions to make continuous and to achieve simultaneous execution. We're going to need a model to do that. So we'll talk about that next.